Good morning. My name is Richard Venditti, and again, this is a lecture in the part as part of the Paper Recycling Advanced Topics course. I'm wearing my red shirt today because NC State's playing the Tar Heels in basketball, and I'm trying to root for the good team. What I'm going to talk about today is screening operations in a paper recycling mill. And we're going to cover all the facets that kind of dictate the efficiency and the fiber recovery that occur during paper recycling. So, first of all, what is screening? Screening separates large contaminants, mainly based on size, but also shape and deformability play a role in screening. So we're trying to separate large debris from the good fibers. And how do we do this? We perform this screening by presenting a barrier to the contaminants and the fibers, actually, maybe holes or slots perhaps, that allow the fibers to pass through and the large debris to be rejected. This diagram right here shows some typical sizes of the slots or the holes that are used in screening. This rectangle right here corresponds to a 8/1000th of an inch slot. Oftentimes people call that 8-cut slot. That's about 200 microns. And what we're interested in this slide is just kind of looking and seeing, well, what particles would be passed through. Okay. Now here we have a softwood fiber, and that softwood fiber is about 3.5 millimeters long and 37 microns wide. And you can see that if it's aligned properly, it will scoot right through that slot. A hardwood fiber, a little bit shorter and finer, has, let's say a typical one, 1.15 millimeters long and 30 microns wide. So that 30 micron wide fiber will easily fit through the 200 micron slot if aligned properly. And then finally we have the fine, and the fines are usually defined as less than 0.2 millimeters, and that will pass through even no matter what alignment it is in. So we can see that all these fibers will pass through this slot. This hole right here is 0.050 inches in diameter, and that's 1,270 microns in diameter, and we would typically we usually think of millimeters as easier unit to think of, so that's 1.27 millimeters. And you can see that all these fines and fibers would pass through that hole very easily. Okay. Now, this slot and this hole are going to remove large debris very easily, like big pieces of plastic or unpulped 5 millimeter wide fibers. What it will not remove, neither of these screening barriers will remove ink particles. And you can see ink particles could be 2 microns to 100 microns as an example. And you can easily visualize that they are going to pass through these openings. A sticky particle is shown right here, and sticky particles are really soft and deformable often. And their size varies from very small to very large. Here's a medium-sized sticky particle. It looks like it's going to be about 200 microns wide. And this would probably pass through the slot and the hole. Okay? And even sticky particles that are larger than these openings might pass through because the forces in the screen may extrude that sticky particle because it's soft and deformable through these openings. Okay, now I want to talk a little bit about the modes of removal that occur during a screen, and let me just kind of read 1 and 2 because they're pretty small. 1 says that stiff particles with all 3 dimensions larger than the width of the slot or the diameter of the hole are rejected, and that's called a barrier device, okay, or a barrier rejection. If all 3 dimensions of the contaminant are big, they will obviously be rejected, especially if it's a stiff particle. The second way that particles are rejected is on a probability, and that's what part 2 says. It says stiff particles with 1 or 2 dimensions smaller than the width or diameter of the slot or hole have a probability of being rejected. Okay? And that probability just depends on what face or what dimension of that object appears to the opening. Okay? So if we have a rod, then one dimension, let's just imagine that one dimension of that rod, like our fiber, is less than that slot size. Okay, so we know that fibers can be very long, much longer than the width of a slot. But if they are presented in such a way where one dimension is smaller, then that would be like the width, the diameter of the rod. If that's presented in such a way, then we can say that it might pass through, it might be rejected. So basically, we've got one dimension where it's, okay, so now let me just introduce you to the axes of this. So on the bottom is the number of screen contacts. So it's the number of times your contaminant has an opportunity to present itself to the opening. Okay, so we go 1, 2, 3, 4, 5. And then on the y-axis is the reject probability. It's the probability that that particle will be rejected in that screening stage. Okay, so we might have 100% reject probability, we might have 0% reject probability. Okay? So what we're looking at here is this let's just look at the one-dimensional rod, for instance. If that one dimension is less than the slot size, then there's 2 dimensions that will be blocked. And we can just crudely assume that if there's 2 dimensions that will be blocked, we've got a 2/3 chance that we would reject it. And there's a 1/3 chance that it would pass through. So basically we've got a 2/3 chance of rejection. Now if that object happens to come back and present itself again to another opening, then we've got another chance that it would pass through. So our rejection probability goes down. And each time it goes down by, we've got 66% reject probability, and then we've got 66% chance of that as our second time. And each time it presents itself, it gives it an opportunity to go through. And you can see that for one-dimensional, very small, we've got this reject probability. Okay? Now for 2 dimensions that are small, we've got 2 chances that it will pass through, and we've got 1 chance that it will be rejected. So this curve right here should be about at the 33% line. So we've got 1/3 chance that it's rejected the first time, and 2/3 chance that it will pass through. And then you can see that we've got 1/3 of 1/3 chance that we'll reject it if it appears twice at the barrier, and then 1/3 times 1/3 times 1/3 for 3 times of screen contacts. So for probability rejection, it depends on how many dimensions are smaller than the slot size, and it depends on how many times that object gets an opportunity to go through that opening. Okay, so this table right here describes the major screening types and the conditions that are used in those screening types. We've got 2 major screening types. We've got a disc type screen and cylindrical type screens, and I'll show you those in a second. The disc type screens are usually used for medium consistency screening, so it could be up to 6%, but up to 6%. And the screen openings are typically holes, and those holes are about 2 to 3 millimeters. So this is called coarse screening. The cylindrical screens, they're going to have holes that are much smaller, and they can have holes, or they could have slots that are pretty fine. And then they also, these are used at much lower consistencies because the smaller openings have a much higher likelihood of plugging, so that we need to use lower consistencies to keep those openings unplugged. Okay, now screening, like I said before, this just kind of reviews actually the two resistances, and I didn't tell you this before, but there's actually two resistances. There's the holes or the slots. Those are a resistance to passage through the screen. And then we've got the fibers. And you might not think of this, but the fibers are also a resistance to passage. And that's related to the consistency. Okay, now here's a picture of a disc screen. Now these screens are usually very close after the pulper. In fact, these diagrams I've taken right after the pulper. We looked at those just briefly before. It's called a disc screen because there's a disc. Let's look at the schematic first. Here's our disc, and there are holes drilled in there, larger holes, 2 to 3 millimeter at least, 2 to 3 millimeters in general. And then we've got a rotor to keep everything moving and actually to clean this screening plate. And the good fibers go through here, and the rejects are maintained in this area. In this case, we've got this is an external detrasher, and basically it's kind of a batch process for a high consistency pulper. So there's that. And then over here, we're showing you another disc screen. That disc is right in here. And actually, this cutaway right here, and it's hard to see, but there's a disc here with holes. This motor right here spins a rotor right here, and then all the, if I could, here comes the pulp in here, the accepts. And for this one, we get spinning like this. The rejects actually go up this pipe. The accepts go through this disc and out this accepts line. Okay, so those are examples of disc screens. Now the other type of screen is the cylindrical screen, and I'm going to spend most of my time for the remainder of the lecture describing how the cylindrical screens actually work. This picture is pretty old, but I really like this picture because you can see the inside and the outside in a very simple way. Very good for learning. So this is our screen right here. And what we have is here's our inlet port, and our inlet port sends the pulp inside this basket. This is called our screening basket. In this case, we're just showing some simple holes. And so the pulp swirls around inside this basket, and the good fiber and the small materials can pass through these holes, and they go out the accepts port, like this. And then the material that we're going to reject, and this is going to include a lot of fibers, because to get the throughput we need and the processing that we need to reject some fibers, and we'll talk about how we save the fibers later. But the rejects actually can't pass through these holes. They fall down to the bottom, and then they pass out this rejects port. Okay? Now the other thing that we can see here is that we've got these foils, and in this case these foils are mounted on a rotor here that holds these foils, and these foils are very close to the face of the screen. You see we've got a motor here that runs a belt that actually turns these foils. Okay? Now the foils have two purposes. One of the purposes is to keep the stock moving and spinning. That's useful in our screening operation. And then the second one is even more important, and we'll talk about that in the next slide. So that's a schematic of a cylindrical screen. Now here's a commercial pressure screen. Just like cleaners, screens can be horizontal or vertical. It doesn't matter. Just depends on how the manufacturer has set them up. Here we have our screen housing right here. And inside here is our screen basket and our rotor type element. Now this pipe right here is our feed. This pipe right here is our accepts. So we're accepting from here. And then our rejects are not shown. Either the rejects come out the back, or this is the rejects port right here. And I'm not clear about that, but so we also have a rejects port. Now here's our motor, and you can see this is pretty big. This is about 2 to 3 feet in diameter. Maybe this is about 3 feet high. maybe 4 to 6 feet long. So we've got a pretty significant motor here running the rotors inside. And one of the nice things about this horizontal layout is that this, in this case, this cap right here can be taken off, and then the basket can be taken out very easily, and maintenance done to the basket. So if there's plugs, and sometimes there are plugs, the plugs, we can open up this cap here, go in, clean out our screen, and fix the problem. Relatively more easy than if this thing was in a vertical position and the cap was on the top. Okay, now what I want to do is talk about what that rotor does that was so important. I told you it swirled the pulp around, that's nice, but the rotor does actually even more than that. That rotor right here is an integral part of keeping this screen from plugging. It prevents the screen from plugging. And what happens is that, let's just say this foil passes at high speed tangentially on the inside or the feed surface of this screen, for example. And what happens here is that that foil, because of its shape, generates a certain pressure profile. So if we looked at one position right here, what would happen? On the leading edge of our screen, right here, we've got a positive pressure difference. So what that means is that the pressure is higher on the inlet than the inlet than the accept. So pulp fiber will be passing through our screen barrier from feed to accepts. Now, this trailing edge of the foil, actually it's got this wing shape, okay? And what's happening here is that it's creating actually a low pressure zone, okay? And if you use Bernoulli's equation, you can kind of see that the velocity here is going to be, well, you can just kind of calculate that the pressure here is going to be lower. And so what happens is we actually get a negative pressure at this part of the foil. And what will that do? That will actually bring material from the accepts back to the feed side momentarily. Okay? So we get this spike in negative pressure. And that is actually a back-flushing action. And that back-flushing action is going to be the mechanism where we keep our face of our screen plate clean. Okay? Without this action, fibers would accumulate on the screen plate in milliseconds, and we would have blinding. And of course, we can't have blinding. So basically, it's like this foil is really saving our hides. Before we had these foils, we couldn't really do pressurized screening like we're doing now. So you can imagine that this foil is like washing your window, but it's actually moving at a very fast speed, meters per second range. 10 to 20 meters per second, for instance. So you can see that it's actually cleaning that basket many times per second. And that is definitely necessary. Otherwise, we'll just get blinding of our screen, and it'll just lock up and pluggage, which is bad. Okay, so basically, the leading edge of the rotating foil accelerates the stock, and that keeps it moving and spinning in the right direction. But it's the negative pulse under the sweeping foil that momentarily reverses the flow, effectively purging the screen openings. And you can see that there's flow in the positive direction towards the accepts before this area, and then after this area right here, we get a momentary negative back flushing. Now, at this point, I'm going to go to our book, and I just want to show you a couple different types of rotors and how they impact that back flushing. So first, let's take a look. Okay. Here are some rotors that you might have. Hopefully you can see these. I'm going to zoom in a little bit. Okay. This is a lobed rotor where you can see that there's like an extension that's sticking out, and then a little, it goes back in. This is a step rotor, and this is kind of hard to see, but there's little steps here, and actually we're showing a series of steps on the top and a series of steps on the bottom. And then finally we've got a bump rotor. Okay, so we've got this rotor, and then we have these little individual bumps, and you can see these bumps are off-centered from these bumps, so we're bumping or causing these disturbances in the pulp mat from these bumps here. And then of course we've got a rotor system, and here's our rotor system. I'll zoom out, I guess. Here's our rotor system. So in this case, we've got the spinning rotor right here, and we've got several foils attached to the rotor. Okay? And those foils will go around, spin around, and they will backflush the openings. The other thing to think about is that these foils actually, if there's, and that backflushing disrupts any type of pulp mat formation that may occur on the face of the screen. Okay. So that's a really, really important part of screening. It's that backflushing and preventing of the blinding of the screen. So we have to have that. Actually, it can cause negative effects too. If that rotor and the consistency, if you look here at this picture, you see that very small gap between that foil and the faceplate. Well, if there's high consistency pulp or medium consistency pulp or even just some kind of fibers there, what can happen is in this small gap there's going to be lots of shear forces that can actually break debris like stickies and make them smaller and make them harder to screen. So we've got issues about that. Okay, now pressure screens can come in different flow configurations. I like to look at, here's 4 different types of screens. In this case right here, it's called a centripetal screen, and it's got inlet side foils. So what's happening here is, here's our inlet, and our pulp is actually going through the screen basket on the inward direction, and our foils are on the outside, spinning on the outside, keeping that inlet side of the basket clean. Then we have a centrifugal inlet side foils. So in this case, here's our inlet, but now the pulp actually, the feed pulp is actually inside the basket. This is much like the picture that I showed you before. This is the same as the picture. The fibers go through the basket towards the outside, and the foils are on the inside, keeping the feed face of that screen clean. So that's what that previous picture was like. Now in this one we have centrifugal and centripetal inlet side foils. So here's our feed, and what's happening here is the feed actually is going to be in this little cylinder or annulus right here. Okay, so right here the pulp comes in this part, and then the pulp actually goes out and it goes in. So it goes both out and in. So there's 2 accept directions. One of them's towards the in and one of them's towards the out. And we've got foils on both this, on the feed face for the pulp going out, and we also have foils for the feed pulp going on the inside. So we're actually, we have, what's the advantage here? The advantage is that we have twice, almost twice, the screening area. So we could have a higher throughput through this system. And then we've got another one where we've got, here in this case, very interesting, we have our feed on the outside, and the pulp is going on the inside. And then the foils are actually, now they're on the accept side. So they've got to do their cleaning by working on the accept side. So they're going to actually, the lead edge of this foil is actually going to push fiber backwards and give that backflushing mechanism. Okay, so why would, what are some of the advantages of each one? Let me just kind of go through it. Centripetal, in this first one, centripetal, where the pulp is going in, because the pulp is spinning, there's forces here because of the rotating fluid. If you have a lot of heavy contaminants, they won't even, because of the centrifugal force, they won't even come towards the basket. They'll fly to the outside wall, and that could help the efficiency. For centrifugal, this one right here, if we have lightweight material, it will stay in the middle that we want to reject. And it can be actually, there can be a special port out the top to remove air and also lightweight rejects. So that's an advantage of this. This one I already mentioned to you. Because the pulp is flowing through two baskets, there's more throughput, so there's there's higher screening face area, so there's more throughput. And then this one, because the foils are on the inside, the foils don't have a chance to break the contaminants on the feed side, so it's a little bit more gentler. And then also we have the thing about if we have heavyweight, high-density contaminants, they're not even going to see the face of the plate. So you can have pressure screens in several different configurations. Okay. Now another important part of the screening operation is how the screen plate is actually built. Okay. Now we already discussed that we could have holes or slots, and these are side views, so you can see they're holes or slots. But the other thing about these screens is that they're usually not just straight through like this. They usually have some kind of taper to them. Now you can imagine that if you wanted to fabricate a screen, it would be very easy to drill a straight hole down like this and then you'd be done. Or to just drill a slot flat down like that. Well, it turns out that with this tapered effect, we get a lot more throughput and a lot less pluggage. So it's important for us to have that taper. But what happened was, as machining capabilities in the United States or anywhere have improved, it's much more, it's easier and more economically feasible to make these tapered type openings that improve our screening. So you will often see tapers on the accept side. Yeah, I should mention, this is the feed side, this is the accept. Feed, accept. And so you'll see these tapers, and then they'll help throughput. Now the other thing that you'll notice for at least slots quite a bit is you won't have a flat surface on the feed side of your faceplate. What you will have is some contour. So here we're showing some bumps here, and here's another type of bump. In this case, the pulp would be flowing from left to right, and these bumps are there to cause microturbulence. They actually disrupt the pulp mat, and by disrupting the pulp mat, what happens is you can get a better throughput through your system. Okay, but the problem with these bumps is that it causes microturbulence, so it gives you some agitation here, and what it can do is take those contaminants that are one-dimensionally smaller or two-dimensionally smaller than that slot, realign them and allow them to pass through. So having these contoured slots help us increase our throughput, but they actually they decrease the reject efficiency if we were to use the same slot size. The answer to that is that people have started to use smaller and smaller slot sizes. Okay, so I have a little animation here. Hopefully that will work, that we can kind of take a look at some very crude cartoons that kind of show what's going on. Now this one right here just says that rigid large objects will be rejected if they simply do not fit through an opening. That's barrier screening. And you can see that the small objects did fit, but the large object that had every dimension larger than the slot width was blocked. Barrier screening. Okay? Now, as I said before, we can talk about contaminants that have either 3 dimensions that are large, like this cube, so all the x, the y, and the z dimensions are large, or we can have 2 dimensions large, like this plate. You've got the x and the y dimensions are large, but the z direction, the width, is small. Or you could just have 1 dimension large, and that would be like a fiber. So here we've got the length is large, but the diameter in both the horizontal and vertical directions are both small. And then of course you've got your objects that are no dimensions are large, and we're not going to be able to screen those out. And when we say large, we mean that dimension relative to the slot width or the hole diameter. Okay, so now we can kind of take a look and see how these different shaped particles, how they will interact with a hole. So here we have a hole. Let's imagine that that's on our screening plate. And if we play an animation, there's a 3-dimension large, there's a 2-dimension large, and there's a 1-dimension large object. So you notice that actually the 3-dimensionally large object will always be blocked. The 2-dimensionally large will always be blocked. But for holes, that 1-dimensionally large may pass through. Okay? So no matter how we align these objects right here, they will be blocked, but the 1-dimensionally large alone might pass through. It just depends on the how it's presented. You see that if the long dimension is presented in the plane of the screen face, then it will be rejected, but if the long dimension is perpendicular to the screen face, it can pass right through, align itself and pass through. Okay? So this actually is just a little bit of a review of what we had before on that other slide. Here's a softwood fiber about 4 millimeters long, and for this one I'm saying it's about 0.04 millimeters in diameter. And you can see that it can pass through a 2.7 millimeter diameter hole, a 1.5 millimeter diameter hole, 0.25 millimeter width slot, or even a finer 0.15 millimeter width slot. Same thing with the hardwood fiber. It's actually going to be 0.02 millimeters in diameter, 1 millimeter long. No issue getting through there. So we understand that the fibers can pass through these openings very easily. Okay. All right, now let's go to a shape, and let's look at the shape compared to a slot opening. Okay. So if we take a look, there's our 3-dimensionally large, there's our 2-dimensionally large, there's our 1-dimensionally large. Now we notice that no matter how this 3-dimensionally large object aligns itself, it will not pass through. However, the 2-dimensionally large and the 1-dimensionally large can align themselves with this slot properly and pass through. Okay? And that's not good. That's not what we want, because this is our accept side. Well, we want the fiber to go through our accept side, but we don't want these plates to pass through here, because these are probably like plastic chips or something like that. So you can see that 2-dimensional and 1-dimensionally large objects can align and pass through. So for this, we have to bring into that concept that probability. What is the probability that this will be blocked? Well, it's basically 1 in 3. What's the probability that this will be blocked? Well, it's 2 in 3. All right, so here we can just show the alignment. Improper alignment blocks it. Proper alignment allows it to go through. All right. Now, the other thing that I talked to you about, and it's kind of fortuitous, we still have this contours up, is these contours, okay? And let's just kind of talk about how the flow affects alignment. So, in a regular pressure screen, we've got our major flow path. Like I said, that rotor is going to, and the way that the feed comes in tangentially is going to cause the pulp to flow in a direction parallel to the screen plate. So in here we've got a major flow direction from left to right. And this is the feed side, and this is the accept side. Okay? So what we can see is that if that flow is nice and steady, that flow is going to align these two types of particles with their long dimensions parallel to this opening. And they'll be rejected. They won't be able to fit through, okay? And you can see that where we have that block, that plate and those fibers passing through, and because they're not aligned. So that's actually good. That's what we want. But what I told you was modern screens have these bumps, these contours on the feed side. And these contours or bumps actually can help us improve throughput, because they break up these flocks of fibers that actually can blind the screen plate. So let's just see what happens when we have these contours. So if I play the animation, that fiber, if it's far away from the surface, it will go past. But if that fiber now, if it is close to the surface and it hits this microturbulence, this is a region where we have spinning. Okay, and we usually have spinning after these microturbulent areas. that spinning actually can realign these one-dimensionally long objects. It will bend them and then pass through. So now you can see that screening can actually separate based on flexibility, because a very stiff particle won't bend and pass through this corner, but a very flexible one will pass through that corner. So basically this microturbulence, because of this surface, is a good and bad thing. It improves our production, but it can actually cause some contaminants and objects to bend and line themselves and pass through. So it's a plus and a minus there. Okay, so alignment. Contoured plates improve the throughput. They can bend the fibers and actually increase the fiber throughput, and they break up some of the flocks of fibers that can blind the screen. But however, contaminants can also be realigned, which is not preferred. And this is compensated by using smaller openings. So that's how that works. All right. Now stiffness. I mentioned it just a second ago. Here's a stiff object. You see it sees that opening, but it can't bend or flex through, and so it gets rejected. And then the flexible object actually has the potential to bend and flex through. So the main flow is from left to right, and you can see that that flexible object can bend through. Okay? So that's one thing. So screening actually will reject stiffer particles more than it will flexible particles. And then extrudability. I talked about the soft material versus the rigid material. That first one was rigid, and here's a soft one. Now, the main reason that material passes from feed to accepts is that there's a pressure difference. That pressure difference is supplied by a feed pump, and that feed pump actually has the high pressure here, low pressure here. Material will flow through, and that's what we want, except for the fact when we have this things like stickies, extrudable stickies, and you can see that that pressure difference is actually extruding that sticky through that slot, and unfortunately it's going to that soft object is being on the accept side. Okay, so screening, it is impacted by size, stiffness, softness, and shape of the contaminants. Okay, so that was just a little bit of some thoughts about what this contoured plates do and how it impacts us. Okay, now just like cleaning, we have to discuss the fact that screening is not a perfect separation. At the throughputs that we use, we cannot design a screen so that we have all clean fiber going one way and all contaminant going the other way. So what happens is we have to reject some fibers in order to meet our throughput demands. Now this graph right here, on the x-axis, it's showing reject rate. So of the feed, how much of the solids, what percent of the solids in the feed is being rejected? And we go from 0 to 100%. And then on the y-axis, I'm showing screen cleanliness efficiency. Okay, and let's think about that. That's the parts per million, or the concentration of contaminant in the feed minus the concentration of contaminant in the accepts divided by the concentration of feed in the concentration of contaminants in the feed, just like last lecture. So it tells you the reduction in the concentration of dirt. Now, what you see is that these curves have this characteristic shoulder, and that this number right here is about 20% reject rate. So if we reject about 20% of our solids, then we can come up to these curves and see, if we reject that 20%, we're going to get about 70% cleanliness efficiency. Okay, and that's good. That's what we want. If we go up to much higher reject rates, then we're rejecting a ton of fiber, and we're only going from 70 to maybe 85% cleanliness efficiency. So we're not getting that much cleaning done, but we're losing a lot of fiber, so that's not good. Now, if we think that we're going to be smart and try and save fibers only by rejecting 5%, then our cleanliness efficiency is too low. So around 20% is a very good compromise between single stage fiber loss and cleanliness efficiency. Now these three, okay, a couple other things about this graph. This dashed line right here is pipeline separation. So if we just had a pipe and a Y, no screening, this would be exactly what we get. So if we rejected 100% of our flow, we get 100% of our rejects. If we rejected 0% of our solids, we would get 0% cleanliness efficiency, for instance. So this is the worst case scenario, and here are screens that are performing better than the worst case scenario. And all it shows here is that this curve right here has the smallest openings, and then this curve right here corresponds to openings that are a little bit bigger, and then finally this curve right here has the largest openings. Okay? So you can see that these curves go down, 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 down with larger openings. So those larger openings are good because of throughput, but they're bad because of cleanliness efficiency. So how could we get a curve that was even higher than this? Well, you might imagine, you might be sitting there imagining, well, if I make my openings smaller and smaller and smaller, that's going to bring this curve out in this direction. That's fine, except for the fact that there's a limitation. We can only make our openings small enough to the point where fibers still fit through those openings. So for instance, if we approximate a fiber as 30 microns wide, then we can only make our openings 30 microns wide. Otherwise, our fibers won't be able to go through our accepts. Currently, if some of the smallest slot sizes are 4-cut or 6-cut. 6-cut is common. 4-cut is pretty rare, but sometimes you'll hear about it. Now, if you think about a 4-cut is 4/1000ths of an inch, and that's just about 4/1000ths of an inch is about 100 microns. There's a simple conversion, and maybe I'll write this on our document. I'm going to come over to here, and I'm just going to say 0.00. Let's just see if I got it. Okay, so I'll zoom out. Okay, 0.001 inch is equal to 25.4 microns. Okay, and so like I said, a 4-cut or a 6-cut are common. Those are these are the finest slots that you can get. They're not common. So a 4-cut is approximately 100 microns, and a 6-cut is going to be approximately, let me do my math real quick, 150 microns. Okay. So if we kind of think about it then, if this is 100 micrometers, and we have a softwood fiber, and I'll just draw a part of it, a softwood fiber is about, let's say 35 microns. What you can see here is that for the 4-cut, we're getting close to having 1 or 2 fibers fit at the same time. So you see as it gets smaller, if we have softwood fibers in there, we've got a very large chance of plugging. So we're getting close to the limits of how fine our slots can be. Okay? And this is a very good conversion to kind of keep in your head. The one that I keep is 1 cut equals approximately 25 microns. Okay? And the other thing to kind of keep in your head is that the width of a hardwood fiber is about 20 microns and softwood is about 30 microns. So 1 cut is about the width of a fiber in a real crude sense. Okay? So we're getting to the point where those slots, some people are using the 4-cut. I've been to recycle mills where they have the 4-cut slots and they've got the baskets on the floor and they've got 6 or 8 cut baskets in actually being used. And the reason why is because the 4-cut plugged too much, and they had just too much downtime and maintenance issues with that. So that's that. All right. Now, we also talked about in our cartoons that what the contoured surfaces can do for us. And I mentioned that the contoured surfaces are in part there to disrupt that pulp mat on the surface of the plate, of the screen plate, and also to realign things. So what happens is this graph right here, on the x-axis, I'm showing pressure drop. Okay, so that pressure drop is feed minus accept pressure. And we've got, to the right, it's a 12 psi pressure drop, and down to the left, it's about 0 psi pressure drop. That corresponds to maybe approximately 100 kilopascal pressure drop to 0 kilopascal pressure drop. And then the other thing that this shows is the y-axis is accept capacity. So that's how much we're getting through our screen. Okay? Now, with a smooth surface, with a cylinder, a cylindrical screen, we get a linear relationship between the pressure drop and the throughput of our screen. Okay? So if we increase the pressure drop, we will increase our capacity. All right? And then what happens is if we take a contoured surface and we look at that, for the same pressure drop, let's say 7 psi pressure drop, this is our throughput for the smooth surface. Here is for our contour. So you see that we get quite a bit increased throughput. So that's a plus. And then this third curve right here shows a heavily contoured surface. And what we get here is even for low pressure drops, we're getting very high throughput. So this just kind of demonstrates to you that the contouring increases our throughput. But we need to realize that the contouring also realigns contaminants and allows them to pass through. So at the same slot size, contouring can decrease our cleanliness efficiency. So the point there is that makes it even more important to have smaller openings, because those smaller openings can compensate. All right, so a couple screen performance variables. This is somewhat of a review. Stock characteristics. What's the fiber type? Is it softwood or hardwood? What's the debris characteristics? Is it one-dimensional, two-dimensional, three-dimensionally large debris? Is it soft? Is it hard? And what's the contaminant level? Because if we have way too much contaminant in there, we'll have a problem. And then we've got the screen design parameters. What is the flow configuration? Is it in to out? Is it out to in? Is it both? What's the plate screening mechanism? Plate cleaning mechanism? Is it with rotors, or is it with a bump, or is it with steps? How gentle or how intense is that screening, that plate cleaning mechanism? Because you can very easily break brittle or soft contaminants, weak contaminants, if that cleaning mechanism isn't very gentle. And then what's the perforation type? Do we have holes or slots? What are the sizes of it? What's the rotor speed? Are they is the holes or slots contoured? Those kind of things. Then operating variables. Stock flow rate. What's the pressure drop across the screen? Increased pressure drop will increase our throughput, but the increased pressure drop will increase the pressure forces that will extrude some of our softer contaminants through. What's our feed consistency? Higher the consistency, the more likely we have a higher consistency mat forming on the face of the screen, and that's going to prevent resistance for flow to the accepts. What's our reject rate? That's going to impact things. What's our screen plate perforation size? Okay, that I would put that up on our screen design. Stock temperature, that impacts our viscosity. It also impacts the softness of the contaminant particles. If we soften those contaminant particles, they may pass through easier. And then there's often dilution flow to the screen. The more the dilution flow, the lower the consistency, obviously, the better the cleaning we get on the surface of the screening plate, and that can also impact our screening performance variables. Okay, and here's just another picture. Screening factors, the perforation size is an issue. The reject rate, how much we reject, is an issue. The flow velocity is important because the flow velocity actually also imparts forces that can act on these particles and make them pass through. The tangential velocity, that's important because the higher that tangential velocity, that suggests that we have more alignment in the plane of the screen face. And then, of course, the consistency. And this picture right here shows it where you've got a bundle of fibers, and that bundle of fibers is actually going to prevent that particle from passing through that opening. Even though that particle could pass through that opening based on the opening size, those fibers are, again, another resistance to that particle passing. We'll see this kind of phenomenon in de-inking washing also be very important. Okay, now I told you that we were going to separate. Screening separation is less than 100%, and because of that, we have to reject some of our fibers. And of course, just like cleaning, we're going to have cascaded systems to allow us to save some fiber. So if we take a look here, here's our feed pump to our primary screen, and that's going to take mix these two flows. It'll go through the primary screen. Our accepts go on into the further on into our process. This primary screen, it's very important that this has a good cleanliness efficiency because this is the gatekeeper. This is actually what dictates how, mainly dictates how clean this accepts pulp is going to our next operation. Well, the rejects from that primary screen are going to be fed to the secondary screen. And now this secondary screen, its objective is to save some fiber. Yes, it wants good, clean fiber to go through to the accepts, but that's somewhat of secondary importance. So this screen right here might have different hole size or different operating conditions because it's going to want to save fiber. And that accept material will go back here, join with the primary feed, and go into the primary screen. And so what we have here is we've got 20% rejects here, and then we have 20% of those 20% rejects here. So we're rejecting only I guess it would be, what is 20% of 20% is, let's say, is 1%, no.
5%?
No, let's just say 20% of 20% is about 5%. That's right. Let's just see. It's 1/5 of 20%. So actually it's going to be 4%. So we've got 4% of our total material rejected. And then here we're going to have 1/5 of 4, so we'll just have 4/5 or less than 1% of our material rejected after our tertiary screen.
Well, why not take the accepts on the secondary directly to accepts instead of sending them back to primary?
Oh, that's a good question. Thanks, Bill, for being observant. I appreciate that. It just depends on your gambling, the amount of gambling that you're going to take. This stream right here is pretty contaminated. So it's got a lot of contaminants in there. So it's got a high contamination level. Now, if this thing, it can either be set up, it can be set up conservatively or kind of in a gambling mode. If it's actually run very similar to the primary screen, then that stream can actually mix with this accepts. But because you have the high contaminant level here, you've got a pretty high probability that you're going to have a lot of contaminants here. So if a mill wants to increase its throughput, then a very common thing to do is just take this stream and just send it on up here with the accepts. So that is a possibility. It's used a lot. In the book it shows a whole bunch of different ways that this can be arranged. This is the most conservative way to run your system. If you want to take some chances, then you can circumvent. For instance, the accepts of the tertiary screen could go to the feed of the primary screen. Or actually, you could have the tertiary, so there are different ways to pump it up, and it's always a question about how much throughput you want, or how careful do you want to be, how confident do you want to be sure that these accepts are clean. So, good point. Very good point. It's like having a real student in here.
I don't want to take any tests.
Okay. You'll just have to write the reports then. No, just kidding. All Another screen that we have, and this is kind of a historical screen, but you'll still see it. That last screen, that tertiary screen, oftentimes it can be in what's called an open gravity or atmospheric screen. And in this case, it's typically just, we've got this bed here, we've got this plate. This plate actually rotates. It shakes. Usually it just shakes. And it shakes. And what we do is we take the inlet, and it's got the contaminants in the fibers. And the fibers can pass through. There's usually slots here. The fibers can pass through, and then we have our accepts. And then we've got our rejects on the top. This is a very good way to recover fiber, but it can only be used for very small flows because we don't really have that cleaning mechanism. So it could be like a quaternary screening stage to recover some fibers. But we can't use it as a primary stage because the other thing I should mention is that for the primary screen, that's going to be taking, and this might not be just one single screen. It could be 2 or 3 screens set up in parallel. So these screens right here are going to have to take the bulk of the flow of our mill, all of the flow of our mill. This one's only going to have to take 20% of the flow of our mill, and this one's going to only have to take, we got this 4% of the flow of our mill. So we can have these atmospheric screens like this in the tertiary or quaternary stages because there's going to be a low flow, and it's got a very simple job of just getting some fibers out. And what happens is all the water, or a good portion of the water, comes through with the accepts. And so what you get is a rejects that is pretty concentrated in debris. It's got a little bit of fiber, and it's dewatered to some point. And then the other thing I should say is showering water and the vibrating nature of this screen, it vibrates back and forth, is what's used to actually move the contaminants this way and to keep those openings unplugged. All right, so it's now we'll kind of summarize. Summary of a pressure screen. Our objective is to separate large contaminants from fibers. And the screens are set up in such a way that we're going to remove some contaminants and protect downstream equipment. It can separate as a barrier screen or a probability screen. With a barrier type mechanism occurring, that means that the contaminant has all its dimensions larger than the openings in the screen. Probability occurs when if you have a one dimension is smaller or 2 dimensions are smaller than the screen opening, then it's basically a probability. What face of that contaminant is going to present itself to that opening? We typically have cascaded stages to save fiber. We talked about that. So these things, we have to reject about 20% of our fiber, and that will give us a cleanliness efficiency that's acceptable. And then typical conditions to promote increased throughput can have negative impact on cleanliness efficiency. So we know that in our case we have this rotor, and that helps us improve our throughput. But actually that small gap between our rotor and our faceplate can break particles or actually cause them to pass through. So that's one case where we're improving throughput, but there's a slight disadvantage in that we can break particles and allow them to pass through from the action in that little gap of that foil. Contoured surfaces are another one. We have a contoured surface to break up that pulp mat that forms on the faceplate. It works in conjunction with the rotor. But also those contours actually realign particles, fibers and contaminants alike, and allow them to pass through. So those are just 2 examples of conditions, and the screening manufacturing people fight with this. How do we improve throughput, keep the thing energy efficient, and yet keep our cleanliness efficiency high? So I've got a little quiz that I'm going to give to end this lecture, and then we will wrap it up. So, okay, so here's kind of a pop quiz, and I think I'm going to have to read it. A particular screening basket is rejecting large spherical objects, but is not rejecting flat disc-shaped objects of about the same size. The openings in the basket most likely are holes, slots, cannot tell from the information given, or could be either. Well, let's see. If flat disc-shaped objects are passing through, that suggests that, and they're large, that suggests that this has slots. Okay, and let me just make sure of that. And that is correct. So slots is the correct answer for that. All right, next question. Whoop. The purpose of the rotor in a screen is to impart rotational movement to the pulp stock, backflush the openings of the screen, both of these or none of these. Well, the rotor does both of these, so let me click on both. And then it says that is correct, so that's good. And then we'll go to next. Which of the following contaminant characteristics impact screening efficiency? Size, shape, flexibility, or all of the above? Well, it's all of the above. We know that. All of the above. That is correct. And I think that's it. So that's the end of our pop quiz. And that will conclude our lecture on screening. Thank you.